Hello everyone, I'm Takkanon from Department of Building Innovation, Faculty of Architecture, เกษตรศาสตร์ University. Today I would like to present a research paper entitled CFD Analysis for Appropriate Positions of Wind Turbines on Tall Building in an Urban Environment. This is part of my student's thesis, ภาภูมิ พิมล วิชยกิจ and I would like to present it on his behalf. Wind energy is one of the renewable sources with the greatest potential for clean and efficient power. Thailand Alternative Energy Development Plan 2015 to 2036 also increases targets for install alternative energy, including wind energy. Nonetheless, urban environment still has some limitations on application of wind turbines. The current research is an initiative to find appropriate position to install wind turbines on tall buildings in Bangkok for best energy performance. The site in Bang Na district was selected for wind studies as it was the business district and close to the main meteorological station. According to Thai building regulations, building height from any point shall not be more than twice the horizontal distance from such point, which is perpendicular to the boundary of the opposite side of the nearest public road. Therefore, the total building height for the study must not exceed 130 meters, as calculated from the 30-meter wide road and height restriction in Bang Na zone. There were 4 options for wind turbine installation, namely Type A, roof installation at height 130 meters, Type B, wall installation. The height installation is at 80 to 130 meters. Type C, in the middle of openings or holes. The height installations are 80, 100, and 120 meters. And Type D, between 2 towers. Height installations between 70 to 130 meters. Each type had subtypes, and each of them was considered for power generation by its average wind velocity. Subtype A1 to A4 were differentiated by rooftop shapes. Subtype B1 to B5 will vary with shapes of floor plan or the building footprint. Subtype C1 to C3 will vary by different sizes of the openings or the holes in the buildings. And subtype D1 to D4 were 2 towers with different distances. The wind turbine location and measurement points were at 3 meters and 6 meters away from the building edge. The study was based on computational fluid dynamics or CFD simulation. The setting condition for wind simulation studies was urban area, which gave roughness, category index, and inverse power of exponent as shown in the table. To avoid the boundary layer effect, we provide computational domain wide enough to put all models in the middle. CFD program SC stream was employed for this study, and in order to generate power, the average wind velocity around the wind turbine must be at least 3 meters per second. We compare both vertical axis wind turbine and horizontal axis wind turbine. In order to generate power, the average wind velocity around the wind turbine must be at least 3 meters per second. From manufacturer's data, we can find relationship between wind speed and energy output of each wind turbine model. There were 196 days of 54% of the entire year that wind velocities were in range of 3 to 6 meters per second. By considering the moderate wind situation in the city, the wind turbine models with cut-in wind speed ranging from 1 to 3 meters per second were selected. There were 10 kW and 1 kW of horizontal axis wind turbine and vertical axis wind turbine. This slide shows the results from roof installation and wall installation. And this slide shows the results from inside opening installation and between towers installation. We found that type D3 gave the highest amount of electricity generated of all options. Amount of electricity generated by each type of wind turbine is shown in the graph. and is related to many factors, including area size, building form, and opening. In terms of area size, it is suggested to install vertical axis wind turbine because there could be more of them in the allowed space. Aerodynamic building forms that correspond to the prevailing wind can induce wind velocities higher than the bluffs one, and providing openings such as in cases of Type C and Type D will create wind channel and steady wind, which is important for electricity generation. Based on the price in 2019, investment cost of each type of wind turbine could be shown in the graph, and we found a list of recommended wind turbine installation such as A1 and A2, D4, C3, and D3. Even though D4 gave the highest amount of electricity, it had the biggest area to consume energy, and the cost of installing 3 of 10 kilowatt horizontal axis wind turbines was high. Therefore, its payback period was the longest. In conclusion, amount of wind energy ranking from the highest to the lowest were D3, B4, C3, and A1 and A2. It's possible to use wind energy in a moderate wind urban environment by installing wind turbines on tall buildings. Positions and types of wind turbines to be installed on tall buildings should be considered as an integral part during building design process. Aerodynamic building forms provide unlimited space for small wall-mounted wind turbines, while installing big wind turbines inside openings or between two towers potentially produce much higher amount of electricity. And that's all for me. Thank you very much for your attention.